Hello everyone. In this video we are going to talk about one of the most common problems in machine learning and robotics, which is finding the shortest path in a graph. And in general, for robotics application would be the shortest path in a maze, correct? For navigation purposes, and there are so many algorithms for solving such problem. One of the most common ones and one of the first ones is the Dijkstra algorithm. So hopefully I pronounce it correctly. That's what I found on Google. So Dijkstra is the name of the scientist from Netherlands, the Dutch scientist who invented this method, really, right? Who came up with this method, amazing method. And hopefully I'm pronouncing his name correctly, Dijkstra. So this method is one of the methods that in machine learning we call it breadth first search, BFS. I'm going to make a video. It's probably my next video in machine learning playlist. Breadth first search versus depth first search algorithms. These are two well-known categories of methods for searching a graph, and in general we call it a graph traversal. So this Dijkstra is a breadth first search, which basically goes at one level of adjacent node for any node and look at all of them, and then goes to the next level and next level and next level, right? So it's kind of like a wave, right? Or ripples that you have on water that goes and covers points based on their distance from the center and spreads kind of in all directions. Depth first just takes one branch and goes all the way to the end of the node before it goes to the other branches. So Dijkstra, the way that it solves the problem is this. I try to go through all of these writings and then later the pseudocode for this algorithm, which you can see here. I got them all from Wikipedia. I'll try to explain them through this simple example here. I guess it's better to go over the graph and explain all the steps over the graph instead of just reading over the notes. So this is how this method solves. Let's say in this graph I want to go from node A to node B, and node B is here. Okay, so from node 1 to node 5 basically. And each one of these edges, which is connecting one node to the other, has a weight, has a cost associated to it. So if you want to go from node 6 to 5, you have to pay a cost of 9 units. From 3 to 6, you have to pay a cost of 2 units, and so on. And all of these nodes you can travel in both directions. Okay? So this is what we call a weighted graph. We want to find the path that goes from A to B, but we want the total cost to be minimum. Okay, this is the goal. How do we go from node 1 to 5 to minimize the total cost? So if I want to just go through it in here, you might say, well, there are so many ways to go from 1 to 5. One is you go from what? 1 to 6, 6 to 5. And the total cost is going to be 14 plus 9, which is 23. Or I can go from 1 to 3, then 3 to 6, then 6 to 5. Here you have 9 plus 2 plus 9, which is 20. Or I can go from 1 to 3, but this time go from 3 to 4, then to 5. This time you have 9 plus 11 plus 6. Or you go from 1 to 3, but go to 2. Then go to 4 and 5, which is worse, right? Because now you have 9 plus 10 plus 15 plus 6. So that is 40. Or you can directly go from 1 to 2, then 2 to 3 to 4 to 5. And pay attention that although they share the same nodes, it doesn't mean the costs are the same. I mean, if you look here, let me do a little bit cleanup. So what is it that you need to add? So you go 1 to 2, 2 to 3, 3 to 4, 4 to 5. So if you add these numbers, right, then you have 22 and 13, which is 35. So you see, they did not turn out to be the same number, although they have the same nodes, because the orders are not the same. Okay, and then, well, last time, again, if you remember, we did this. We went 9, then we went 10, then we went, instead of 2 to 4, which is a huge weight, right? We did 9, 10, 15, and 6. So the last option that you have is to go to from 1 to 2, but from 2 you directly go to 4, and then to 5. And here you have to add these weights together, which is 13 and 15, that's 28. So you can list all possibilities like this and then say, well, what? This is the best path. Correct? Now, if you do it this way, we call it the basically brute force search. So you are looking at all possibilities and then finding what? Finding the best path. Well, you can do it, but the problem is when the graph gets bigger and bigger, this kind of searching all possibilities become very time consuming. There is no intelligence in that. You're just looking at all possibilities and then finding the best one. Again, for large graphs and big problems, this is going to take a lot of time. So what Dijkstra did is this. So here I did a little bit of cleanup also. If I call node 1 the start point and node 5 the goal point, this is what Dijkstra does. First of all, it assigns a distance of infinity to all nodes except for the first node. The start node, it gives it a distance of 0. Any other node, it gives it a distance of infinity. Also has a queue called visited nodes. So in the beginning, you started empty, and then once you check each node and the surrounding nodes of it, the connecting nodes with it, you add it to the list. So what do I do? First, I am at the start point, node 1. So I look at all the nodes connected to it, nodes 6, 3, and 2. And look at the cost for going from 1 to each one of them, which are what? 7, 9, and 14. So the first thing I do, I clean up the current distance at these nodes from whatever it was, which was infinity. Now I change it to what? To 14, to 9, and to 8. To 7, I'm sorry. Okay? And since any node that is attached to node 1 has been updated. The distance for them has been updated. Now I say I have definitely visited node 1. And the distances for them is going to be like this. It's going to be node 1 is 0, node 2 is 7, node 3 is 9, node 4 and 5 are infinite at the moment, and node 6 is 14. Okay, so each one is for node 1, node 2, all the way to node 6. Now, what would you do next? You say among these nodes, which one locally sounds the most promising, the least costly? Well, among these, except for the start node, you don't care about this one. This is your start node. Among the rest of them that are not infinite, which one is the least costly? Well, definitely it's 7, between 7, 9, and 14. So my next target is going to go to point 2. And I'm going to check in the vicinity or in the connections of node 2. So from 2, so now I go from here to here. Now from 2, where can I go? I can only go to 3 and 4. I cannot go back to 1, right? Because this is just defying the purpose. So I can go either to 3 or to 4. If I go to 4, what's the cost? So if I want to go to 4, the cost going 2 to 4 is 15, but ultimately all of these distances should be measured from the start node, because my goal is to go from start node to each one of them. So going from 1 to 4 means what? 7 plus 15. So now this guy should be updated, this one, this node 4, to 7 plus 15, which is what? 22. What about node 3? If I want to go from 1 to 2, 2 to 3, I have to add what and what together? 7 and 10, correct? So now you have to add these two together, because this is the path you are going. The total of that becomes 17, but right now I have a cost of 9 for it. Am I going to replace that 9 with this 17? No. I only replace 9 if the new number, if the new path from 1 to 3 that I got gives me a shorter path. Because 17 is bigger than what is already exists, what is currently existing, I'm not going to do that, and I'm going to keep 9. I'm not going to update it to 17. Now that the nodes connected to 2 are also updated in terms of their numbers, which are 3 and 4, and 1 was already there, so now I add node 2 to the visited nodes. So now 3 stays at 9, and 4 goes to 22. This is still infinity. 2, the best bet is 7, okay, and 9 and 14. Okay, so now node 1 and node 2 are visited. What do I do next? Now I go and look at my new numbers. So let me put them there. Again, among all the numbers I have, except for the start node, that are not infinite, which is 7, 9, 22, and 14, which one should I look? Now, you might say, well, at this point, you should also cross this number 7. Why? Because you already added that node to the list of visited nodes. So 7 is out of the picture. You already visited node 2 with the cost of 7. So 7 will be eliminated. So now the decision is between these 3 numbers. 9, 22, and 14. Definitely you would go with 9. So the next place to go is to visit here. Then from 3, where would you go? So from 3, 1 and 2 are already visited, so you can only go to 6 or go to 4. If you go to 4, what's going to happen? Well, guess what? The cost to reach 3 at the moment is 9. If you want to go from 3 to 4, you have to add an 11 to it. So that changes the cost of 4 to 9 plus 11, which is 20. And if you go from 3 to 6, now the 9 that you had to add a 2 to it, so it becomes 11. So between 22 and 20, which one is smaller? 20. So you definitely update the weight of node 2 now. So now that 20 was less than 22, I change this to 20. The same thing here. 11 is less than 14, so I update this to what? To 11. Okay? Right? And since the nodes connected to 3 are already visited, so now 3 comes to the list of the visited, and 3 also gets out of the picture. So now you're down to what? The remaining nodes. What else do you have? So the remaining nodes are 20 and 11. Now the promising is 11. So I'm going to come here. And now what? 6 is connected to 1 and 3, which are already visited. So I'm not going to care about these 2 edges anymore. I only care about this edge, which has a weight of 9. The current weight at 6 is 11. 9 plus 11 is 20. So now this weight that was infinity at the goal, now it changes to 20. So this number is now going to go to 20. Right? And that's it. There is nothing else connected to 6. So now 6 is going to be out of the picture. We consider it visited. And the weight for 6, which is 11, should also be crossed. Now, should I proceed any further? Well, first of all, at the moment, the goal node, which is here, has been reached. The weight of it is updated. But is there any better path? Well, what can I do? Here I only have 2 options left, nodes 4 and 5. But guess what? 5 is the goal. 5 you are not going to assess. So the only option for you to check if you want to is node 4. But look here. The current cost to go to 4 is 20. The best cost to go to 4 is 20. The best cost to go to 5 is 20 also. So even if I can go from 4 to 5, the only way that I can get a path better than what I currently have is that the weight of the node going from 4 to 5, this guy becomes 0. And this does not happen with Dijkstra, because Dijkstra is to find the shortest path search in a graph where the weights of these edges, all of these weights, should all be bigger than 0. Okay, if these weights are not bigger than 0, then we cannot use Dijkstra. So I can add it here with positive weights of the edges. Okay, so that's the only way that you can use the Dijkstra algorithm, is that the weights of the edges are positive. If they are negative, then you have to use the Bellman method, and that's a separate video. So even as I said, if I want to consider that and I want to look at the possibility of going through 4 to 5, then I have to go and visit 4, And if I visit 4, the only thing that 4 has not touched yet is 5, which has a 6, so that makes this guy to be 26. And now, because that's 20, which is the current cost plus the cost of edge from 4 to 5. And am I going to replace 20 with 26? Of course not. So even if I visit 4, it is not going to give me a path better than what I currently have. So the problem is solved now, and I have visited all of the nodes except for actually the goal node is already visited, kind of, because you already changed the weight of it through node 6 and 4. So at the end of the day, 5 is also visited. And if you now look at the final distance value that I have, 0, 7, 9, 20, 20, and 11. What are these numbers? These numbers are the shortest path that you can go from node 1 to any other node in your graph, right? So the fastest way to go from node 1 to 2 has a cost of 7. The fastest, not the fastest, the best, the smallest cost path going from 1 to 3 is 9, which is going from here, right, directly to here, 9. If I want to go from 1 to 4, the smallest is 20. How? 20 comes from this path, which is 9 plus 11. If I want to go from 1 to 5, the best is 20 again, which is this path here. Going from 1 to 3, 3 to 6, 6 to 5, which is 9 plus 2 plus 9. And finally, if I want to go from 1 to 6, the best is 11, and that is not going directly from 1 to 6, but actually going from 1 to 3 and then 3 to 6, which is 9 plus 2. Okay, so this distance at the end of the day gives me the shortest or the best path, the minimal cost path from the start node to all of the other nodes. But guess what? My goal is node 5. So this is the minimal cost. And what was the path? If you remember, I just told you the best path is this path here. This one, going to this one, going to this one, which is sum of these 3 numbers. Correct? So how do I exactly output in my code this path? I know this number is 20, but this 20 corresponded to which one of the edges that I should travel from 1 to 5, right? Which one of these edges exactly corresponded to this minimal cost 20? So the first part that you see in the pseudocode, this part, is just responsible for giving you that distance, the distance thing here. This part will give you the distance vector, and it gives you the visited vector. But it doesn't give you the path. It's the second part of the pseudocode that can give you the path. And I can tell you how the second part will work. So let me tell you how to get the path once you have this distance. Okay? Okay, how do I find it? Well, if I want to find the path, this time I start at the goal. I say the goal is node number 5, so I start here. Okay? I start here. And I look at the distance is 20. And again, this is node 5. This is the last node of the path. For now, I put it as the first one, but then at the end, I fill it the path to make it from start to end, not end to start. So I start at the end of the path, which is the goal position. And I said, okay, to this node number 5, which nodes are connected in the graph? So for that part, I need something that is called adjacency matrix. The adjacency matrix will tell you which nodes are connected, or between which nodes you have an edge. So if you go and look at this, there is a 5 and a 4 in it, and there is a 5 and a 6 in it. Okay, because 5 is only connected to 4 and 6. So I say fine, 5 is connected to those two. So now I go over for going from 5 to 4, 5 to 6. What are the associated costs? 6 and 9. First, I go and subtract this 6 from the current minimal cost. So I say 20 minus 6. The cost should be 14. Is there any of these nodes for which the cost is 14? I don't see any. So I neglect this. The next time I subtract this 20 from the other edge weight, which is 9. So this time I say 20 minus 9 is 11. Is there anything, any node in this list for which the cost is 11? And I see one. There we go. What node is this? Node number 6. So it is definitely node number 6, the next node, because it is connected to 5, first of all, and second of all, if I subtract the cost of node 5 minus the edge connecting between 5 and 6 and get 11, 11 does exist in my list. So definitely the next one is going to be 6. Good. So now what is the number I should focus on? It's not 20 anymore. Now it is 11. And 11 is for which node? For node 6. So now I focus on node 6. Between those that are connected to node 6, first of all, which nodes are connected to 6? It is 5, which I have already considered in the path. The other two nodes that are not in the path and connected to 6 are what? 3 and 1. Between 3 and 1, the way I go from 6 to 3 or I go from 6 to 1, the costs are 14 and 2. The current minimum cost is 11. So I should subtract this 11 from 1 time 2, 1 time from 14. I can definitely not subtract from 14, so this is a dead end. This one becomes a 9. Is there anything in the list with the cost of 9? Yes, that is 3. And guess what? With that 2, I can go to 3. So definitely my next one is going to be 3. Now I'm at the cost of 9. So now I will focus on 9. Again, connected to 3 are what? Connected 3 are 4, 6, 1, and 2. Correct? And between these, correct? So 3 can go to 4, can go to 2, and can go to 1. First of all, remember at the end of the day, the last one should be 1. Because this is your start node, this is your goal node. But should I directly go from 3 to 1 or go, let's say, maybe to 2 or 4 and then go to 1? How do I know that? Well, the cost right now is 9. So I should subtract this 9 from the weights of the edges connecting 3 to these guys. 3 to 4 is a what? 3 to 4 is an 11. 3 to 2 is a 10. 3 to 1 is a 9. Which one can I subtract from 9? Only the 9. 10 and 11 cannot be subtracted from 9. And so the only possible solution is to go directly from 3 to 1. And that's it. So the path is going from, now what? This is the kind of Philip path. The real path, now you have to do a Philip. So the real path is going to be 1 to 3, 3 to 6, and 6 to 5. This is your actual path. Okay, which we talked about it. It's like this. So you start at the goal node and look. See from the nodes that are adjacent to it, which one, if you subtract the cost of the edge between them from the list distance, it gives you a valid number in the distance vector again. If you get a number, that is your next node to go backwards, and then you keep going backward, backward, backward until you end up at the start node. Once you are at the start node, guess what? It is over, and now you can fill up the path and call it your optimum path. So you can get the optimum path, you can get what? The vector of minimal distances, and the good thing is once you have this vector of minimal distances, now if you decide not to go from 1 to 5 but maybe go from 1 to 4, you can still what? Repeat this process, but this time if you want to look at the best path from 1 to 4, you look at this distance, which is what? For node number 4. Okay, you start with this one and redo the path calculation. That gives you the best path. Or if you want to go to 6, you focus on this number. You start with that number. So just pay attention that this distance is all calculated for one start node, and the start node here is what? Node number 1. And then for all other nodes, it found the minimal distance from 1 to those nodes. Correct? Minimal cost. This distance is the minimal cost from node s equal 1 to all other goal nodes. And if you pick any of them and you do this reversing process, you can find the optimum path going from 1 to any other node in the graph. So hopefully this Dijkstra algorithm is clear, and here I have written some code for you. In the first code, I have calculated basically for you the same graph that you see here. This very same graph that you see in this picture, I created it and I calculated the path for it and I highlighted on the graph. So let me run it for you. I should have run the first section. Let me run the first section. Here. So if I put it side by side, you clearly can see it is the same graph, right? 1, 2, 3, 4, 5, 6. And the weights of the edges, you see from 1 to 6 is 14, from 1 to 3 is 9. So all the weights are also shown, and then this is your best path: 1 to 3, 3 to 6, 6 to 5. And the way I did it here, you basically define the connections. So one edge goes from 1 to 2, one goes from 1 to 3, one goes from 1 to 6. Then you have 2 to 3, 2 to 4, 3 to 4, 3 to 6, 4 to 5, 5 to 6. You use the command graph and you pass to it the beginning and the end of the nodes, the end of the edges. The command graph will create such a graph for you. You pass the weights using graph.edges.weights, and this is the adjacency map for it. You can also get it using the command graph.adjacency. And this is the start node, this is the goal node, and here I plot the graph for you with the edge label and then the weights of the edges. You see here I'm starting all of my distances at infinity, and then at the start node I make it 0. First I make my current node here. U is a current node, is the one that you're investigating it and the connecting nodes to it. That is U. So U is the current node. I started at the start node, and then as long as U is not equal to G, so I have not reached the goal node, I keep going. Okay? I find all the connections, I find the visited, and the visited, I update the weights for them here. I only do update the weights if the new weight is less than the previous weight that you found, which you can see over here. And then I find the promising node, the minimal distance. I mark the one that I have visited and keep repeating. Once I found it here, I start finding the path. I say the first element in the path is the goal node, and then I keep going back until I haven't gone back to the start node. So here again, I do that process that I mentioned for you. And finally, I flip it from left to right, and then I highlight the best path on the graph with a red color. You can do the exact same thing. This time I did it for an image. So this image is a maze here, and it is gonna do the same exact process as the Dijkstra. The only difference is for the image, when you go from one pixel to the next, there is no weight associated. So when you move from one pixel to the next pixel, right, the weights are, all of them are going to be 1. Basically, it's the amount of the number of pixels that you have moved. So for searching an image of zeros and ones, when ones are free spaces to move, zeros are like obstacles. So anywhere that I can move to, as long as it's a 1, I move to it. And the cost of moving from pixel to pixel is only 1, so all of these weights are going to be 1. The difference for an image is there are a lot of these nodes. Each pixel in the image is like a node. Okay, so when you do apply the Dijkstra for an image, for doing a navigation of a robot going through a maze, you have a lot of nodes, but the weights are all 1. Okay, so you see here I'm adding a 1 to them each time I move. As I told you, any node, any pixel which has a value of 1, so you're free to navigate through it, is what we call a collision-free workspace. Each pixel in that is a node. So if I say find all of the pixels in the image that are equal to 1, the answer, if you look at the size of it, is 3470. So you have something close to 3,500 nodes here. It's not like the previous case that I only had 6 nodes. I have close to 3,500 nodes. And so looking through an image takes a little bit more time. But the good thing is the weights of all edges are 1, so this update part of the distance vector is going to be done a lot faster. So this is the code that I will share with you. You can find the download link for it under the video description, and hopefully I could show you how to use the Dijkstra algorithm to find the shortest path in a graph where all the weights of the edges are positive numbers. Thank you, and I will see you in my next video.